So for our next speaker, we have Dr. Zlatko Minev, and he's with Google Quantum AI and associate fellow at CFAR. And he used to be at Young Quantum, and he got his PhD from Yale University with Professor Deborah Ray right here in the audience. Zlatko is very well known for his work on acoustic metal and also for his experiment on detection of quantum jump. So without any further ado, let's give it up for Dr. Zlatko.
Thank you. I think that applause belongs to you. It's what, 4:30, we're half an hour behind, and you guys are still in this room, and you look completely awake. I think you're mutants. So thank you so much for keeping it through the day. I love the energy in the room, and I hope to keep it up. I had several lattes with hazelnut pump today, so I am full of energy right now, and we're gonna have a lot of fun. Michelle has already set up many controversies for us to tackle. I may touch on them if you provoke me. And this is your talk. So I have about 90 slides. I expect to get through about 5 of them. My ambition is not to cover everything, even though it is to give you a big picture overview. My ambition is to uncover at least a little bit for you in the words of James. So I do believe our organizers need a huge, huge thank you and appreciation. There was a lot of blood, sweat, and tears that I watched firsthand. I'm not including myself. I mostly just gave suggestions and they did all the work. In putting this together, this doesn't just happen. I mean, look at this amazing stellar lineup and crowd. This is a really unique workshop. Nothing like this that I know of has happened focused on quantum device design specifically. This is the first one. I hope it will be the first of many. So thank you guys, especially all the student organizers. You've really made this possible. Now, you'll see a few of my initial slides here. Oh, thank you. A few of my initial slides will overlap with the beginner track, but then we're going to take a completely different tack. And I'll go into the big picture. And we're going to cover a lot. Kiss metal, energy participation ratio, lumped element oscillation quantization, and how to use them in practice. So that's a lot. But let's get to know you first. Who here has used a quantum device? Raise your hand. Everybody, great, you're in the right room. Analyze, made one? Most people, great. Who here believes that the flux is an unwrapped variable, not a non? Okay, oh, Eli, good. All right. So we should actually take an actual poll one day. Let's start with the very big picture for a second, and then we'll go into the details. You've seen many, many pictures of devices. Here's one from my current new employer, Google. These are XMON chips or transmon qubits. You've seen many qubits. I want to go over what a readout or qubit is. But what's important that every, I think, speaker has highlighted, and Michelle did a beautiful job in illustrating, is that we tend to use different levels of abstraction to understand these systems, and they are all important. And you have to get a little bit of a handle intuitively and maybe mathematically on some of them. We have the lumped element picture with the quantization, which Michelle just gave a beautiful broad introduction to. We have the qubit and Hamiltonian picture. We have the distributed electromagnetic picture and the layout, the GDS level. These are all the building blocks. And the beautiful thing is, I made this analogy earlier, these are a little bit of a Mexican restaurant world where you pretty much use the same ingredients to make different deliverables. You have capacitors, inductors, junctions. That's it, actually. There's not much more. Some resistors and transmission lines, but they're just infinite LC ladders anyway. So, you know, three elements. Let's call them 4 to be more fair. The junction, the inductor, the capacitor, and the transmission line. You know everything. No facelifts. I mean, I'll leave that for another day. So these are our building blocks. Now, how do we design classical processors? There is a level of abstraction. There is a hierarchy when you talk about VLSI or anything like this. There are a lot of levels of abstraction. So if you look up a textbook on classical chip design, you'll see that there's a hierarchy that starts with nature. You then go to the laws of physics, so think Maxwell's equations. Then you actually go to our favorite topic that Michelle just covered, lumped circuit abstraction. Then you go into digital abstraction, logical abstraction, memory abstraction, finite state machine, micro, blah, 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 right? It goes on until you get to JavaScript. And actually, it doesn't stop there. It keeps going. Where's the quantum level version of this? Anyone have one? Okay, so let's build one. Oh, by the way, there's also spec sheets. There's, these things, eventually, you don't, when you do a high pass filter, you buy one for mini circuits, you're not usually thinking about nature. So we do need these levels of abstraction as we get more sophisticated. So what are the levels of abstraction for quantum circuit design to go from a chip that looks like this, pieces of physical metal, to actual Hilbert spaces, Hamiltonians, which honestly we don't really care about directly anyway, because now we're at the level of, as Andreas showed us, logical qubits. So how do we begin to bridge these? Well, I would propose the following fundamental quantum device design layer abstraction levels, if you want. On one side, you start with the quantum processor. That's the thing that you see in the cloud. If you log into IBM Cloud or other clouds, you see a architecture that looks like this. You say, I have some qubits, I have some connectivity. That's at the highest level for the user. You go down to the bottom, you have all of our friends in bunny suits who make these beautiful Easter eggs. I'm not sure that analogy makes sense, but it's 5 p.m., so let's keep with it. This fabricated device is first made in a layout file, which you then have to send to your friends in the foundry, or someone needs to pour a lot of blood, sweat, and tears into it. You then have to ask yourself, how did I come to this? Well, usually somebody or a few people run a lot of HFSS simulations. Anyone use HFSS in here? Oh my God, everybody. Anyone not use HFSS, but something else? A few hands? Well, you can use HFSS and you use something else. Anyone? Okay, you're all about to become experts in something else tomorrow in the workshops. So Shanta will tell us more about that, and Murat is here. Then you go typically level of abstraction higher, which is what Michel spent his talk on, which is quantization methods, lumped element, quasi-lumped element. Sometimes you can't do everything with lump. See, this is a quasi-lump. It's a one-dimensional transmission line, right? That has a different functional form. And then you go one level higher. This is where we have huge armies of amazing theorists and people like Jens Koch, who really pioneered a lot of this as well, which is how do you deal now with the quantum Hamiltonian that you get? Because that's quite a complicated beast. Certainly, that's the most quantum thing you can think of. And then you actually have to think about gate evolution. What do the pulses look like? How do the frequencies combine, right? And you can spend a lot of time engineering that until you actually get a CMOS gate. Okay, so there are a lot of layers of abstraction, and it's really an industrial effort at this stage with hundreds of people sometimes, where you have to go up and down this bridge, just on the fab side. I mean, it's a massive effort. So how do we automate this and make it easy, and also maybe even democratize it so that it's more accessible, so that we can fuel that fire in the furnace of innovation, because we need to deliver on quantum computing. My personal attempt at this was to start Qiskit Metal, which is an open source Apache 2.0 highly permissive license, open source Python package that tries to link all these layers exactly in this way. And so you can go up and down. It doesn't tie you to ANSYS or any particular render. It's made so that you can have, in fact, you use it with AWS Palace tomorrow. In principle, you can do other softwares like Elmer and so on. We have a render for that. It also plugs in with, it doesn't live alone, right? There's no way we can do everything. It also plugs in with Jens Koch's SE qubits. It uses QTIP. There's now squads from Eli. There's SQD Metal. These are other packages that have developed over time. So there's a whole ecosystem that's growing that we hope you will be part of and contribute to. I want to acknowledge Shanto for single-handedly pushing a lot of this here. Let me pause and just acknowledge this is a miracle. The fact that this works in the first place when Michel Devoret did his PhD, I won't say the years, but I'm not sure anybody thought this. I mean, people didn't even know that a junction was quantum. In fact, I think Michel was, one of the first, maybe the first to ever prove that. Basically, was the first to prove that with your team at Berkeley. So in a way, we have to thank you, Michel, for giving us all bread today to work on these things. So I do believe it's a miracle that we can not only do this, but we can do this with incredible precision at the level of design that you demand, well, let me rephrase that my bosses have demanded for me. In industry, we're talking about energy scales that are 10 to the minus 6 parts per million. When you fit that chi, that dispersive shift, that can be 100 kilohertz or 50 kilohertz on something that is 6,000 megahertz, right? That's subparts per million. That's the level of precision we are at, and guess what? We only need more. So I believe we need to get better and better at this and optimize it. I think Eli has taken a wonderful thing to begin to do machine learning on top of this. That's why I have tried to connect all these layers, because you need to ask a question up here at the top and try to optimize at the bottom. That relationship is highly non-trivial. Good. Any questions? Just one. Okay. Yes. It's a wonderful question. In fact, this picture taciturnly assumes that in the back, but it's not explicit. At every layer, you have to worry about noise. And, focusing on the Hamiltonian a lot only is really not doing justice to the story of design. In fact, half the job is optimizing the Hamiltonian while you optimize dissipation. In fact, the reason we have the transmon, the fluxonium, and other qubits is because of noise. Otherwise, we just pick one and stick with it. But you want to deal with different kinds of noise, try to find ways to get around noise. So that is why we have such a rich landscape of qubits. So some of these methods are very much on the place dissipation and Hamiltonian engineering on the same footing. In fact, I developed the energy participation ratio with Michel in Michel's lab, Michel Devoret's lab. That method talks about how much energy is stored in an element. That's the only question you ever ask, other than, is it in phase or out of phase? And from there, you can reconstruct the full Hamiltonian, but you can also reconstruct the full dissipation budget. You can ask, by asking how much energy is in the dielectric of the substrate, and you know the dielectric has a loss tangent of 10 to the minus 6, you can calculate the error budget there. Then you say, what about the metal vacuum interface? What about the metal substrate interface, right? All these interfaces have different dissipation ratios. So in fact, engineering those is what led to the transmon being macroscopic. Otherwise, we'd make the transmon, 70 nanometers and call it a day from a single junction. But no, we can't do that because the dissipation ratio, the energy participation ratio in the lossy materials is too high. So you dilute the energy participation ratio by making it giant, 200 microns wide on the pads, and you reduce the surface loss participation. You have a high quality, long-lived transmon. That's a very abridged story. Eli. Thank you for correcting me. Yes, all the credit goes to Shanto. Eli sponsors it. Yes. So thank you, Shanto. And you will have a full workshop on it from Shanto on Wednesday. Oh, the machine learning is even sooner. Great. By the way, Michel and I tried to do circuit quantization in ChatGPT, and we did find problems where it fails. So you still need to listen to these lectures for now. So my message is, I think this is a miracle. What I also find incredibly encouraging is how global and empowering this community is and has been. So again, I'll focus on the parts that I know of this. So I'll focus on Qiskit Metal. First we have a huge library of dozens of tutorials in all these methods and all of this. We're going to talk about a maintainers meeting, so please find me, Eli, Jens, or you guys, Shanto, to talk about joining the open source side of this. And I'd like to highlight a few works. So for instance, here at the Niels Bohr Institute, the Squid Lab, in fact, I think Ben and Due Christian, am I saying that right? Due, thank you, are in the room. They were kind enough to provide me with some very recent designs they made in Qiskit Metal and actually fabricated. I don't even know what this is. It's a 5-tunable, wait for a quantum device that they've made with these open source tools. I'll show you several more versions of these. This one looks very cool, by the way. I love the diagonal feature. That's very cool. Some of these are fabricated and made, maybe even all of them. This one, I believe, is also from Chris Warren, who's been a longstanding contributor. This is an SEM image of an actual device fabricated and made. It's kind of warpy here, but I want to give you a sense of the fact that people are doing these in their labs. They're using these open source tools. They're building and developing on top of them. So a lot of what you're learning here, that knowledge is going to be very useful. And you don't need to build everything from scratch. You can begin to contribute back to the community. So also want to acknowledge very much Shanto and Eli here. These are some of their designs in Qiskit Metal. They've measured these devices, they've cooled them down. They've built a lot of this expertise, this know-how into the tools and are making it public and available to you. Again, Figen, I believe, is maybe on the call if it isn't 5 a.m. or where she is at the moment. She's made Fluxonium, analyzing with the energy participation ratio, extended that framework to the Fluxonium. Oh, Figen, yes. Thank you so much, Figen. What time is it where you are? And they've made some beautiful. So forget and everyone on the web who is up at 1:40 a.m. or any time that isn't daylight. Thank you so much. We really appreciate you guys. Huge kudos to you. So again, more example chips, beautiful data extensions, things I never had the time to try or learn or do. Other people have now carried the torch forward with. Well, the story goes on. Here's even more designs and experiments and cool downs. This one's we made at IBM for Tokyo University's TU Delft. There's some Chalmers measured experimental data, etc., etc. That's my ecosystem part of the adventure. Any questions? All right, let's get to stage one of designing qubits. So let's focus on the totally classical, the most mundane, the most boring thing, which is still incredibly important, and that is layout. Let's start with that and then build up. I could have gone the other way from the top down, but I'll start at the bottom. And I will post all these slides. I have earlier versions of these slides here, but all these slides will be available, and I think the organizers will make sure all of the slides of all the speakers are online. So coming back to an example chip, what is our greatest ally in chip design? Arguably, it's regularity. You look at this structure, again, it's sort of the same ingredients stamped and repeated. Okay, so if you understand the building blocks, I believe you can go quite far. That also allows us to focus on reuse, fine-tuning, automation, and extensions. What do I mean by that? I mean that if you go on this webpage, you will see that all of the designs you've seen in the talks, I believe, today and yesterday, including from Andreas Walraff, I think this is his design. I didn't make it, somebody contributed it in the open source community. I'm not even quite sure who, but you can find out. The XMON design, the regular square transmon design, these are pre-built components, fully parameterized. Meshing is automatically determined for them in Qiskit Metal, including more seeding of the mesh on the junction. Like all these best practices are generally built in. You also have qubit couplers, this MIT style coupler, you can just stamp down. Again, I didn't build this, somebody in the community did and contributed it. I encourage you to do the same. If you don't, you're an evil, I'm kidding. Then you have direct couplers, you have bus couplers, there are many variations. as you get more and more rich. And I think Squads, if I'm saying that right, has even more designs that Shanto and Eli have put in, and Shanto will do all the machine learning on tomorrow. Then you have input-output couplers, right? These are sort of the basic building blocks: qubits, resonators, couplers, input-output. That's pretty much everything. I'm probably missing something, but this is basically everything you need ingredient-wise. And there are many variations. I've just listed a few here. So let's pick one. This one I like because I'm familiar with it. That's how you build it. Anybody here use the Q components in Qiskit Metal before? Okay, I see a lot of hands. Wonderful. By the way, I apologize if you ever had problems installing Metal. I know it's quite rough. There is a, I see a lot of heads shaking. There is a version 0.5 standing in pull request 1002 that is going to solve all those problems and is up to date, including PySide 2. It's removing dependencies. It's no longer using Conda by default. It will use virtual environments, which will make everything faster. But I need help to finish it. So if you look at pull request 1002, and we will get it merged in there. Yes, and I see you two guys are nodding your heads, because I think you've been on that pull request. Then what do? Well, you know, this is all classic. So I built this Qiskit Metal GUI, and then the team helped expand it a lot. You don't even need the GUI. I think you will use it without the GUI tomorrow, just fully scripting, but there's 2 workflows we support. It's very much like any GDS cell. You can parameterize your transmon. You can put parameters. What's nice is you can programmatically adjust these from your Jupyter notebook in real time or from the GUI. So you have this dual workflow. And you can vary the geometry any way you want. And, you know, there's a lot of other features. There's, of course, the notion of pins or ports. So when you link components, you say link some qubit 1 port D to qubit 2 port B, for instance, so that you have this pin-like structure, and you can auto-route. Here's an example of placing 4 transmon qubits on a chip. Naturally, we don't put all the transmon qubits with their dipole moments oriented in the same direction. Half of them are rotated, so you have less crosstalk between them. Then you can say link this. There's a Qiskit Metal function that says, you know, link pin 1 qubit A to pin 2 qubit B and auto route with a meander of this length, and that will roughly give you the right frequency for that bus coupler. Then you can add some launchers as well. You can draw them like this programmatically. You can auto CPW route to particular places on the line. There's a table of all the geometry if you want to see. There's some global variables you can adjust. Again, this is all fairly standard stuff. What are we doing here? Oh yes, we're exporting to GDS. And then you can export this to GDS. Right? This is the flow of at the bottom. This is how you do the layout, for instance. It's not the only way, but that's one way you can do it. If you want to import GDS into Metal, that's one of the most asked questions. I believe Eli told me Shanto is making something.
I got in Shanto's way from too much work to make something until someone takes it.
Okay, so SQD Metal has some stuff. Good, good. You work on SQD Metal. You've been using. Excellent. So apparently now you can import GDS into Metal as well if you prefer. Or you can use a couple commands. So if you're capable enough to use subtract and add geometrically, you can build any component you want. And I believe all of you can do it. So we built a smiley face qubit. Okay, that's it for layout. Any questions? Michelle? The question is, what about flip chip techniques? So there is actually a flip chip. Do you want to comment on this? No, please. There is a flip chip capability built into Metal. We did not explicitly develop it very far, but some of the community members have allowed it, you can define multiple chips. So you can define a layer stack with multiple chips and have multiple layers on it. Of course, when we built this, there were very few groups who could do flip chip technology, but now there are more. And I think you guys are you using flip chip? Yes. Yeah, maybe just introduce yourself briefly to the room. We might as well make it's a small, intimate audience.
And I think definitely this is a promising platform for scaling quantum devices. So it's also going to be
Thank you. So this is one of the directions we would like the community to help extend it, or the community would like to help extend it. So the base for it is there, the fundamental abstractions are built in, but all the tooling on top is not. Excellent. So now we get to part 2, which is the actual quantum analysis part. So this is where the fun really begins. Everything we saw so far is classical. You can do it in Cadence. You can do it more or less in any tool. Okay, now we're going to go up the levels of abstraction from the layout to the E&M simulation to quantization to Hamiltonian. The reason we ended up building all this stuff in metal at the bottom is to have a tight link from the quantum Hamiltonian and be able to say, to link the design and nudge things or modify this while looking at the results at the Hamiltonian. So you can do machine learning on top of this, for instance. Let's start with a simple example where you have a transmon qubit coupled to a readout resonator. And you ask yourself, what is the Hamiltonian and what do the wave functions look like? Okay, how can you do this? Well, as most of you know here, there are many, many ways and techniques. Michel certainly has blessed the community with his article in 1997, which is still the go-to reference on circuit quantization. So at the most fast level, you can write down a white box lumped circuit model. Of course, you have no idea what those values are precisely, or you sort of have to find some way to extract them from the layout. That's a big question mark. But once you have this lumped model, you can follow Michel's lecture notes and derive a Hamiltonian. If you want to go slightly less abstract, a little bit more realistic, you might model the resonators as actual distributed 1D structures. They're one-dimensional, but they're distributed. So I call this quasi-lumped because it's basically lumped, but you have these one-dimensional distributed resonators. And this is in fact quite useful and needed. You see that in some of the IBM chips I published on, we needed to take this into account. There were certain renormalizations that happened from the way that the eigenmodes get renormalized due to the capacitances, the loading capacitances here. So sometimes you actually need this. And then you can go to the full glory and beauty of Maxwell's equations, where you're simulating Maxwell's equations. And you can either use impedance methods. So this is this Simon Nigg and team paper from Yale. And then I would say you also have the energy participation ratio, which is really just the dual. At a fundamental level, these two methods are just two sides of the same coin. It's like the Heisenberg picture and the Schrodinger picture. They tell you the same thing, but they are different pictures. And some things are easy in one, and some things are easy in the other. And you might find one more intuitive or the other. So generally, I would say these give you the most. In fact, I would argue the energy participation ratio gives you by far the most information, because you find everything about the dissipation, the way the energy profiles are distributed, in addition to doing the Hamiltonian at the same time. And there's a rich library of open source ecosystem that goes along with this, because this is a lot of work. This is a lot of methods. And each method, you don't just read the paper and implement it. There's all these little things and tricks you have to know to make sure it does the right thing. So I'm happy to see that people are developing this because we'd like to really make it a consortium, make it a foundation, and really build this into a sustainable ecosystem. Okay, so let's look at how you use these methods. So in many cases, you look at a linear model, a linearized model, just as I think Michelle introduced and noted. You might render your design into a software like ANSYS HSS for AWS Palace, or Elmer, or GDS Mesh, or anyway, other software where you have the qubit and you have the resonator as a 3D structure. You may even include things like wire bonds, as you see on this CPW. You can do an eigenmode simulation and say, okay, what is the eigenmode? And you see that if I plot the electric fields, essentially all the electric fields of the transmon qubit eigenmode are located at the qubit between the plates. But there's, spatial profile. Most of the electric field is concentrated between the pads. That's the surface that matters the most for the quality of the chip. Or you can do quasi-lumped methods where you look at an extractor like Q3D or some other simulator to actually write down a white box model. So you can represent this qubit resonator as a transmon qubit coupled to a transmission line that is loaded at one end, because the loading will actually change the eigenmode structure. And of course, you can do impedance, which is just a dual of eigenmodes, so I don't have a big box for it. Now, let me focus on two of these techniques, because I can speak a little more to them, which are this a quasi-lump model, and then I'll talk about eigenmodes. And we can pick our adventure as we go and see how deep we want to. We can really get into the physics. I'm going to try to give you a bigger picture overview, but slow me down, please. So the paper reference is here, and let me walk you through an example. You have a big chip. You have your 10,000 qubit chip, and you want to say, what is the Hamiltonian of this chip? Now, if you're Michelle, you will insist that I have to simulate the whole structure, and I think that's important. But if you also are poor on time, you might say, well, what simpler thing can I do? And let me take an approximation. I won't cover all the box modes, and let's say maybe I'll miss out on a few features, but let me zoom in on one piece of the chip where I have a transmon qubit that has some charge. What does it have? It has it's coupled through a bus resonator here to another qubit. This is the readout resonator over here, coupled to a readout line. I have another bus coupled to another qubit, and I have a charge line here. And this is basically what the IBM chips used to look like when they were still public. Now, you can kind of color code this visually and say, well, I know what the purple box is. You have seen it 10 times by now. It's a transmon qubit. I know what the Hamiltonian is. I don't need to solve it again. We've done it 10,000 times. You can say, I know what this green thing is. It's an oscillator. I've solved it 10,000 times. And you can say, well, I know what this brown line is. It's an oscillator. I've solved it 10,001 times. You can say, I know what this blue thing is. It's an oscillator. I solved it 10,002 times. That's pretty much the oscillator, transmon, Fluxonium. That's about it. So they're simple, well-understood building blocks. You don't want to reinvent the wheel. So the idea is, let's see if we can write down the Hamiltonian of the transmon separately from the Hamiltonian of each of these. You already know that H3 is A dagger A. You already know H1 is A dagger A. There's no question. The question is going to be, how do they talk to each other? How do they renormalize each other exactly at the level of 10 to the minus 6? So how do we do this? Well, one way you can approach this, again, you will not get all of the uplinks here. There will be non-local effects that you're going to miss out on that if you really want to do this at an industry scale, you may want to take into account, is to break up your chip into cells. So we'll call this cell 0. You can cut out this region and say, let me only simulate this region. Why this region? Because the capacitance between these two pads is going to be renormalized by the fact that there's a piece of metal right here, and a piece of metal here, and a piece of metal here. That's going to change the distribution of the electric fields. Let me then also, in fact, these guys, they're such linear good harmonic oscillators, I don't even need to simulate a coplanar waveguide unless my meanders are really narrow, right? If this meander bend is very close, then the electric and magnetic fields from here will couple to the ones here. You're going to have some capacitance from this to this. It's not, it doesn't look like the characteristic impedance will change. But if I make my meanders broad and generous, you know, this is just any transmission line with a characteristic impedance. So let's break it up piece by piece. Here's actually, this is from a paper of a real chip design. So this actually represents a physical device we made. You can export this through Kismet Metal into Q3D in this case. You know, Metal will automatically give you a cold, you know, dielectric for the base. It will give you all these sheets. It will add what's a thin conductor, et cetera, et cetera. So all the boundary conditions, all the meshing operations are already set in place. Then once you mesh it, and you know, this is at some number of iterations, you see that there's a higher energy density around these structures. So that's why the mesher has automatically increased the meshing around these pieces of metal. We now have a structure that it looks like what Michelle showed us. It's just a circuit network. There are nodes. And in Michelle's language, each of these metallic islands is one node. And each node can talk to every other node through a capacitance. There's a certain conservation law that says that the diagonal is related to the off diagonal in some way. It's just the sum. And you can extract each of these values to very, very high quality in this static regime using one of these simulators, and then you write down a circuit. Now the circuit is a little complicated because it's everything couples to everything. But you've all been to Michel Deborah's lecture, so you know how to solve it. I'm sure some of you have already written down the answer. There is one little twist, which is that, of course, there's a Josephson junction here. There are no inductors or no junctions in many of the nodes. So in Michel's language, some of these nodes are active, some are not active. You also have to be a little careful because some of these nodes are coupled to the transmission line. And the transmission line has inductance. So you need to make sure that that's addressed in the right way. There are some nodes that have, you know, there's only one active node here. The other one's not active. But it's also not the ground node. So in the language of classical mechanics, this induces a holonomic constraint in the equations of motion. In other words, it's just a constraint equation that you have to eliminate. So the reduction of abstraction is from a distributed circuit to a lumped element circuit that has non-active nodes that you can then eliminate. Absolutely. So this is a purely static simulation of the capacitance matrix. Of course, you can ask, is this the right capacitance matrix at 6 gigahertz? And you know, it isn't. But because our structures are pretty big and distributed, and 6 gigahertz is not that high, you know, 6 gigahertz in free space is what? 3 centimeters is 10 gigahertz. In free space. Now this has an epsilon of 10 roughly dielectric, so changes the frequency, but these are pretty big features, so it's quite in the quasi-static regime. Second, I clearly have not included the leads here, and you can include them, and of course you can try that, but you know, it's not that big of a renormalization. But these are orders of paranoia. And then you can ask yourself, what matters at my level of paranoia? And the answer is that tomorrow's level of paranoia is higher than today's. So eventually these things matter more. But for the experiments that I did at the time, this was good enough. Yeah. Oh, Yes, absolutely. So some people are very religious about rounded corners versus sharp corners. I take a more agnostic view on this point, but certainly a lot of the designs you see in Kismet metal are rounded. In fact, if you saw against Fluxonium, I believe it was rounded pads on both sides. Okay, so at this stage, we've reduced it to Michel's circuit quantization. We know how to deal with active and non-active nodes. And in a way, all this paper does is follow circuit quantization carefully. It turns out that when you do it for a general circuit, there are a lot of hair pulling bugs you can run into. Technically, you just follow the procedure, but it's easy to miss or get confused or do something wrong, even though it looks very simple at first. But this took me months to actually work out correctly. But strictly speaking, we're just following the same procedure. There's no new physics here. So then once you have this model, what you do is to write down the systems that you care about. And in fact, we know that the transmon is just effectively described by this junction and these two nodes. Then you have these distributed structures, which are over here. Now, by the way, notice that I haven't said, oh, my resonator is a transmission line. That doesn't fit the model. It's not. It's a transmission line loaded by a capacitor. I can't reduce this to a transmission line without a capacitor because there's always a capacitance to ground here that's larger. And that that can be a huge load in a lot of devices. So you have to map onto the right system. But we know exactly the Hamiltonian of this. It's analytic. You can write it down analytically even. So at the end of the day, from what this lumped element model does is from the circuit, it gives you, without any approximation, no approximations at all, it gives you the Hamiltonian of the transmon, which, by the way, this capacitance here depends on every single capacitor in this network, in principle, right? So you can have a capacitance hop. The charge can kind of hop between many of the nodes and then come back, and there's an effective dressed capacitance. Most of the time, it really only matters what these two guys are, but the rest of them dress it, and they can lead to non-local effects. The same goes for the effective capacitance here, and how you get that, you have to be careful with to do the decomposition in the right way at the right time after you eliminate these holonomic constraints, but the paper does that in great detail. So what we have are effective system Hamiltonians that are dressed. They're dressed. They're not just, you don't just take this purple capacitor, you take a dressed capacitor. That's really where a lot of the care goes into. And you can write down your total Hamiltonian as a system Hamiltonian. It's just the sum of the individual systems dressed by all the coupling. So they already include coupling. They're dressed parameters. So this interaction doesn't act, there's already interaction accounted for, but it's kind of trivial interaction in that it just renormalizes at a classical level the parameters. And then you have the actual quantum interactions between these dressed systems, which will dress the systems yet again. So think of a cold winter with several layers of clothing. This is where we can now use basically Jens Koch SC qubits and put in any system you want, whether it's a transmon, fluxonium, 3-junction flux qubit, 0 pi qubit, cos2 phi qubit, et cetera, et cetera. So here we just use open source ecosystem. We use Jens's package to say that we have a box and we understand what that box is. The way we then formulate the interaction Hamiltonian, in this case, it's all linear coupling. It's just, X, or, it's charge coupling typically, or flux. And this picture includes everything. It includes the dressing of parameters due to couplings. It's non-perturbative. I mean, there's no perturbation theory here. It's exact. It includes all non-local couplings. It includes all holonomic constraints. It includes all non-dynamical degrees of freedom, quasi-distributed structures. It includes the A-squared diamagnetic contributions. There's a number of papers in the community that deal with problems that don't exist if you sort of follow this procedure carefully, right? Good. Any questions on that? Yeah, Eli?
How do you make sure you're connected?
Yeah, great question. So I didn't exactly explain it, but that G comes directly from a procedure, a series of steps acted on this matrix.
I guess what I'm asking, typically the way we look at that involves some ratio.
Yes. Yeah, that's a very tedious procedure, but it's in the paper and it's in the source code. I don't have a short answer. It's just we tested it, we did it. It took many months and it seems to work. In fact, I can prove it works theoretically too. So that's really the idea of the quasi-lumped element oscillator. It's one technique that is in your toolbox. It's not the only technique, but it's a technique that can be very powerful for many different devices. Any questions? Oh yeah. This is. Yeah. This is really a throwback for me. It's like 6 years ago that I wrote this paper. It's great you looked at the experimental table. I have actually the experimental data here in a few slides because I will show you real device data. How well does the prediction work versus the experiment? And you'll see that you have to ask, what's the error budget? You have to ask, what matters? So I think I literally just would vary one of the parameters, such as maybe when we get to the experimental slide, I can answer that question. But that is a sensitivity analysis, essentially. How much do my ultimate values that I calculate, like the chi, the dispersive shift, depend on these effects? Like, what if I change where I didn't tell you where to make the cut, right? I said nothing about that. It's kind of like Heisenberg's cut. He didn't say where to make the cut. I also don't tell you where to make the cut. But you can ask yourself, how much do my values change as a function of where I cut the chip? And they will change. But the question is, does it matter? And that's the kind of sensitivity analysis we did in the paper. But let me get to the experimental data on that. Okay, so if you're not satisfied and you don't want to just think of reduced equations called quasi-static methods or static methods, but you really want to explore the glory of Maxwell's equations, their full finite element detail, you can employ, for instance, this energy participation ratio method. Now, I'm only going to sketch here. I think it's a very beautiful physics. I'm only going to sketch it in the interest of time, but I'll start with a question. What's the Hamiltonian of this shape? Anyone? Imagine electromagnetic fields in a box. What's the Hamiltonian? Okay, if you don't know, you're flunking hardcore right now. A dagger A, good. Anyone else? Anyone? A dagger A, good. All right, let's see. This is a trick question. What's the Hamiltonian of this shape? Okay, good. Anyone object? No? Michelle, objections? A dagger A, good. Okay, what's the Hamiltonian of this thing? I've put in some lumped element inductors in my distributed structure. Anyone? Same? Okay. See, you can all do surgical quantum molecular dynamics so easy. There's no magic. It's always A dagger A. If anybody asks you in your sleep, just say A dagger A. It's always the answer. So why do we have a conference on this if it's always A dagger A? It's super simple, right? In fact, the only thing that HFSS does is figure out what is A dagger A in terms of the distributed structure. How do I write A dagger A as a function of the physical mode? What's its sort of spatial profile? Now, if you have a nonlinear dipole, I think Michel introduced the idea that you can write a Josephson junction, or for that matter, any nonlinear element that depends on flux, a nonlinear inductor. You know, if you can take a Taylor series, you don't have to, but you can. And this is not an approximation. I can just break it in two. There's no approximation. I'm just going to break it into, I'll keep all the terms to infinite order. Okay? And my point is that I'm going to break up my system into a linear and nonlinear piece. I'm going to break it here, and I'll put the linear pieces in HFSS, or my finite element. All the nonlinear stuff I'll tag on later. So what's the Hamiltonian of any circuit? Well, it's always A dagger A. We established that, especially if the circuit is linear. So all I do, I don't care what the circuit is, give me the hardest circuit you can think of. The linear part of it is always A dagger A on M modes. Doesn't matter if it has a facelift junction or if it's anything else. Now, I would claim it's A dagger A. Of course, the real question is, what's the nonlinear part? That's the hard part. But you see, the nonlinear part doesn't care about the full circuit. It only cares about the junctions. It doesn't care what the rest is. Like, who cares what's happening in the transmon box? The only thing the nonlinear part cares about is what's happening in the junction. It doesn't care about the input-output directly. It just cares about the junction. So it only depends on phi j, which is the reduced flux quantum operator across the junction. So what is that? Well, I can take a cavity mode. So this is now ANSYS HFSS picture that I plotted. This is so old, it's from my time in Michelle's lab. So thank you, Michelle, for sponsoring this project. So here are the electric field contours, and there's a little, you see there's a chip of a transmon here, but this is a 3D transmon. This is so sort of in the early days of the transmon here. This is what the cavities would look like at the time. And you see that the electric charge on the surface is just oscillating. Red means there's a lot of charge, and blue means there's very little net charge, and it's just charges flowing from the top to the bottom across the seams of this cavity. The same thing happens if you have this planar structures. There's no real difference. It's just that now it's flowing across the bridge more directly. And you can zoom in to the qubit structure, which in this case looks like two metal pads separated by a junction. Someone will complain that's not what a junction looks like, and you're right, but you know, it doesn't actually matter. You can ignore what the leads look like, you can ignore most things, you can just put a rectangle, and for 90% of transmons, that's good enough. Sometimes you have to take into account the lead structure, you know, the leads look, they have some shape, they have some inductance, but most of the time you get away with this. Of course, you can increase your paranoia. And as you know, in the transmon, all of the current will go through the junction port, which here is just modeled as a lump element RLC boundary in ANSYS. And you can look at the current. And then you can say, well, I can calculate in my classical software how much energy is stored in the junction as a fraction of the total energy in the mode. In fact, the total inductive energy. But you might say, okay, that's good. So what does that tell you? That tells you how much energy is being sucked up by the junction, right? This is an energy participation ratio. It goes between 0 and 1. That's it. It can't be larger than 1, can't be smaller than 0. 0 means the junction doesn't participate. 1 means that there's no other inductor. And you can work this out for a classical circuit. You can work it out for a distributed circuit, lumped, doesn't matter. And it's always the same thing. It's 1/2 Li squared. That's the energy of an inductor. That's what a linear inductor energy is. With phi squared over 2L, it's the same thing. Divided by the total inductive energy in the mode, which you can work out. You know, in HFSS, you can do the field integral if you want. Your.
Yeah, so this is a.
Oh, wonderful question. So now I've kind of swept that under the rug. Here, it's the inductance of the junction element, which in this case, in the numerical modeling, is a special boundary condition, which implements an effective inductance. So it's I think it's called an RLC boundary, right? It's an RLC boundary. So it's basically a sheet that has a special boundary condition that enforces what an linear lumped element inductor would do. So it enforces that, across the terminals of this, you draw a line that says this is the line of the voltage. This is what I mean by voltage. This is what I mean by current. And make sure that the relationship is enforced, that phi is Li here, essentially. Physically, it originates from two sources. The inductance originates from the kinetic inductance of the Cooper pairs in the junction, and also the magnetic inductance that's associated with both the current and the leads and just the electric field profiles. For a transmon qubit, the kinetic inductance dominates. Almost all of the inductance is the junction. The linear inductance of the magnetic field is very small. So in fact, if you draw a loop around this is how I actually came across this whole energy participation ratio idea in the first place. Is, I said, let's go back to our textbook. If I draw a loop and I integrate the field around the loop, I should get the current. And you don't get the right current, or you don't get the right energy. That's because the inductance is actually stored in the kinetic energy of the electrons, not in the magnetic fields. And in fact, HFSS sort of reproduces that for you. So really here, it's the kinetic inductance. Yep. The question from Michelle is, how do you take into account the kinetic inductance of the pads? So the good news is that for the most part, that doesn't matter at the current level because it's very, very, very small. Of course, if you have leads, that can have higher kinetic inductance. And then you can begin to model that at several levels. I mean, one, you can put an ROC boundary, from some analytical model to model that. Two, QRaptor or some of the newer software actually takes into account London's equations and takes into account superconductivity. And I think the kinetic inductance is built in there, if I'm not mistaken. So I think the newer softwares actually can account for it directly in the finite element simulation, which is probably the ultimate thing you want to do. That's right. Well, in practice, what you do is you say, I actually don't know what LJ is, or I'm designing LJ. I want to design LJ such that I get the qubit frequencies that I want. So in fact, this is either a fit parameter or a variational parameter that you optimize for some target parameters. Yes. Quick question, yeah. Yeah, these are great questions. So great. So we really have a very awake and bright audience here. Thank you. The question is, I talked all about renormalizations earlier. The junction is going to hybridize the modes. So in fact, this is not what the current distribution of the transmon looks like. This is because from the nonlinearity, there will be linear mode renormalizations that hybridize this junction mode, linear junction mode, to other modes, other linear modes in the purely linear way. Maybe in Michelle's talk or in my earlier beginner talk, you saw that the nonlinearity can, because of the commutator relationships of A and A dagger, will give you lower order renormalizations. So a phi to the fourth term will give you an A dagger B coupling between a mode A and a mode B, which is the same thing as a linear coupling. So in fact, the spatial mode profiles here are just all they do is they serve as a basis in which to write the full Hamiltonian. And that's what I'll explain. And it doesn't really matter that they're not exactly the right basis, they just happen to be a really good basis. And then it's on you to make sure, as the user of a method, that you're including all the modes of relevance. And once you do that, everything works out. But you have to make sure, this is just the basis in which we're doing an expansion, nothing more. As you mentioned, these fields are not the right fields. They will be renormalized by the hybridization through the nonlinearity, which is purely quantum. You can't get that classically with other modes. But if you simulate all these modes, all of that will be coupled. And technically, you could take all these fields, renormalize them by the right values, and plot them again. I have never done it, but somebody should. And the beauty is that all this works out anyhow, as long as you include all the modes. So we know that, again, we know A dagger A. Everybody knows A dagger A. We always get that. The dual to that is not for the energy, but for an operator. So for the position operator, no matter where it is or what it is, if I ask you, what's the position operator in quantum mechanics, you should always say A dagger plus A. That's just by construction, works out. So we know that this is quite a general statement. I can also, if you look at the energy participation ratio paper we wrote, we formally derived this expression through the Lagrangian, if you were in the beginner track with me today. You know, we walked through these steps of the Lagrangian, a Hamiltonian, a Dirac canonical quantization, etc. So we did that formally, but you could have guessed this on day one, that it's a linear combination. Basically, the voltage across the junction is the sum of the voltages across the junction due to every mode. Wow, voltages add. Okay, perfect. Very close then. The critical component here is these 0-point fluctuations. In fact, the entire problem of circuit quantization boils down to asking what are these parameters for junction J and mode M. And the way that I like to answer this or think about it is through this bridge. And this is a derivation you can do on a napkin in 3 lines. Since we're short on time, I won't do it. But you can prove to yourself with literally on a napkin that the reduced flux quantum fluctuations, this is the same thing as the variance of the 0-point quantum fluctuations, normalized in the right way, is just the ratio of the mode frequency to the junction energy, scaled by the participation. So if the junction participates a lot, it has very large 0-point fluctuations. If the junction does not participate, the 0-point fluctuations are small. So from this, by just calculating this quantity between 0 and 1, you can write down the anchromonicity of the qubit. The dispersive shift is just a mode overlap of the energy participation ratios. You can write down the lamp shift. You can reconstruct the full spectrum of the transmon qubit. What's very important, and this is not obvious in the impedance picture, but is very obvious here, is that these are participations. They're numbers between 0 and 1, and of course they're constrained. They are entangled. In fact, if you've heard of entanglement monogamy, there is a very corresponding equivalence here to EPR monogamy. So Charlie Bennett, you see a Qiskit seminar with me and him where he talks about entanglement monogamy. This is kind of the dual for circuits. So the commandments of energy participation ratios are that all modes and all dipoles are created equal. Each dipole has exactly 1 unit of EPR that it can dilute across the modes. Dipole here means junction. Each mode receives exactly one EPR unit, so across all its inductors. In the interest of time, I won't walk you through them, but I'll just say that what this means is that you cannot build any circuit you want, any Hamiltonian. In fact, we tried to do this for my dissertation and quickly found out that there are very fundamental constraints, and this is the quantum jumps experiment with the dark mode and the bright mode. You can't have a fully dark mode. And that follows directly from the constraints on the energy participation ratio. So everything comes down to the energy. Someone asked about, what about dissipation? To calculate the dissipation is the exact same question. So you can define a lossy dissipation ratio, energy participation ratio, that tells you the Lindbladian. So this is the overview of the protocol. Essentially, you can write, by the way, you can have any nonlinear element in here. It could have multiple junctions, it can be flux bias, etc. You can do any of them. You find the eigenmodes, you calculate the energy participations. In general, you have to also get a sign, which is +1 or -1 for each junction in mode, because you have 2 junctions in the in phase or out of phase. That will matter for the Hamiltonian. And then you can write down the general Hamiltonian with no approximations at all. This is not a quadratic approximation. You can do any, like to any order. And and basically calculate the full system. The main issue is, can you get all the modes of interest? And you can also calculate all of the different lossy and energy participation ratios. I won't go through them. They're all automated in IEPR and Qiskit method. Right, there's many different losses. Oh, we won't have time for the controversial discussion, but I will just leave you with the idea that everything I've said implies that the flux is an unwrapped variable. I never thought of really anything wrapped at all. There are advantages, of course, to thinking of wrapped variables, but it's the dual. It's the dual of having, if you have a cosine potential, which extends to infinity, and if you've ever taken any, semi-advanced physics class, you will have learned of Bloch bands and Bloch waves. And so what you get are Bloch waves and Bloch bands. And you see this in numerical diagonalizations. If you take 10,000 Fock levels and you write down the transmon qubit in this Fock basis, you will see that the wave function of the ground mode looks like this. So if you have very few energy levels, you just see that it's Gaussian. If you've taken many energy levels, you see that it looks like a mode, a Gaussian that's in every single well. And it has a profile because we've done a finite analysis, we've truncated the Hilbert space, so it's finite extent. So it looks like it's in a well itself. So that's why you get this curvature. But if you look at the eigenvalues, you see that you get Bloch bands where you have, the ground state has many eigenvalues, 25 in this case. The one level has 25 eigenvalues. And if you look at the transition frequencies between these, you will exactly recover the charge dispersion relationship that Michel introduced for you in the last lecture. And you can precisely calculate the dispersed, what's here, it's 12 kilohertz dispersive relation. This is, by the way, what we measured in the experiment. It's exactly this number in experiments as well. And each of these levels only talks to one other level in the band. So there is super selection happening. I won't go through the beautiful experiments other than to say that if you do the experiments, so this is now on real experimental data from my time at IBM on IBM chips that you've probably used in the cloud. These were pretty hard chips, so the LOM analysis did very well at fitting the measured chi to the predicted chi, but it was about 7% off. And then the eigenmode and driven modal more or less agreed at the same precision, so they're more precise. So if you do eigenmode, if you do full wave Maxwell equations with impedances, it's more precise than lump models. Not by much for these devices, but it is better. So the final stage is, I've covered a big picture. All these methods exist, but you don't need to rewrite the code. I encourage you not to, unless you really, really want to understand what's going on. But get ready for some hair pulling. There's tutorials on each and every one of these things and more covered in this code base. Also, I didn't talk about impedance, scattering matrix analysis, but some of that is in there as well. Eigenmode analysis, capacitive analysis, quasi-lumped analysis. It's all pretty much largely automated. There are pieces missing, of course. We haven't done every single combination, but these are just example pictures of rendering, meshing. You notice how there's extra seeding of the mesh here and here. So all these practices are built in with Qiskit metal. So we try to do also render in a native optimized curve in HFSS, et cetera, et cetera. And then you can also make reports and plots of convergence rates. You have to be very careful about convergences of your qubit frequencies and harmonicities, finite element meshing, how many, is my cross-current converging, is my G-coupling converging? So if you do metal.analysis.lumpmodel.analyze, it will plot all these for you. And my last slide is an open call to you. This community cannot exist without your help and contributions. I'll highlight Shanto, of course, here for being blood, sweat, and tears on your end, that you will also introduce us to tomorrow. Murat will give us a wonderful also lecture tomorrow. He's not in this room, he must be in the other room. And we've been having discussions with Eli, we're roping in Jens now. I think you saw some of the beautiful results from you guys as well. It would be great to have the kind of open source ecosystem and support it so that the whole field can benefit and life can be easier for everybody. So if you're interested in contributing, if you're interested in being a great citizen and being highlighted in my slides with your picture, this is the one incentive I can, oh, maybe we will even have a scholarship with money. So if you're interested in money, contact us. Thank you very much.